Welcome back to Math 103. This is video number 11 on growth and finance. Suppose that you deposited $1,500 on January 1st, 2010 in an account that paid 3.5% annual interest, where the interest is being paid once a year at the end of the year on the money that's been in the account all year long. Suppose you had the good fortune to do your business at a bank that increased the interest rate to 4.75% on January 1st, 2012. How much money was in the account on January 1st, 2015, assuming you made no withdrawals? Big assumption. All right, so we have two approaches here. One is to do this step by step in the same way as the previous example and keep track of how much money is in the account every time something changes. It's going to turn out that for this type of problem, where the only thing that's changing over time is the interest rate, there actually is a shortcut, and it can be done all in one step. Let's do it the step-by-step way first. You start out with $1,500 in the account. At the end of the first year, you multiply once by the one-year growth factor to get $1,552.50. That amount of money sits in the bank all year long through 2011. So that amount gets multiplied at the end of 2011 by the one-year growth factor. And that gives you $1,606.84. Notice that actually that 2-year span could have been handled by a single multiplication by a 2-year growth factor. Okay, because you've got 2 years worth of growth captured by this one expression, 1.035 squared. We continue to consider the effect of interest payments, but now the interest rate is increasing for the remaining years. So you take that $1,606.84 and leave it in the bank for 3 years. We're counting now from the end of 2011 until the end of 2014. That's 3 separate years now of being multiplied by the new interest rate, 4.75%. So the amount of money at the end of 2011 experiences 3 separate growths at the end of 2012, 2013, and 2014, and that ends up with $1,846.86 in the account. That's on the last day of 2014, and it's still that same amount on the first day of 2015. Notice that there actually is a legitimate shortcut here. There wasn't when we made withdrawals along the way, but in this problem, it's only the interest rates that are changing. It would have been completely legitimate to take that initial $1,500, multiply twice by 1.035, then 3 times by 1.0475, and if we wanted, just compute this as one single expression, we would have gotten the same answer. All we did in the step-by-step method was separately multiply by these individual growth factors, so we're allowed to put them all together into one single expression. We'd like to make this study of interest payments a bit more realistic. Realistically, when you have money in a savings account at a bank, it pays interest on your account more often than once per year. And it's certainly the case that if you owe money to a lender, for example, to your credit card company, then your account balance is almost certainly accruing interest. That is, you are accumulating more debt more often than once per year. That means, in other words, your account balance at the credit card goes up not because you've just bought something new, not because you've borrowed additional money, but just because your debt is sitting there accumulating interest. Your debt is growing, and that growth is occurring more often than once per year. It's not just on the last day of the year that they charge interest. Okay, they're charging interest along the way. So what does it mean for an APR of 4.5% to be, as we say, compounded more often than once per year? Your credit card will quote an annual rate of interest, but there is actually something going on all through the year. To understand this, suppose that you deposit $3,000 in an account with an APR of 4.5% compounded monthly. The idea here is that the bank takes that 4.5% annual interest, that is a whole year's worth, and it breaks it down each month into 1/12 of 4.5%. Why 1/12? Because there are 12 months in a year, and we're talking about monthly compounding. right? So if 4.5% is 1 whole year's worth of interest, then a twelfth of that is 0.375%. That's 1 month's worth of interest. So instead of multiplying the account balance once per year by the full year growth factor of 1.045, instead the bank multiplies your account balance every month by the 1 month growth factor. So that's 1 plus the monthly rate as a decimal. 1 plus this 0.045 over 12. In other words, 1 plus 0.00375. Right? This 0.375% converted to a decimal is 0.00375. To say that this 1.00375 is the monthly growth factor means that every month the bank, as it were, presses the pay interest button on its computer, which causes your account value, whatever it is as of that moment, to be multiplied by 1.00375. That is, to grow in value by 0.375%. So instead of doing this once at the end of the year and multiplying by 1.045, it 12 times a year multiplies by 1.00375. Please go on to the next video.